Every other video on the internet about color is wrong. Because what they all say is that when light interacts with an object, some of that light is absorbed, and what isn't bounces back off at your eye, and that's what you perceive as color. But that is leaving out the most interesting part. That is like saying that the reason why a car goes forward is because you push on the gas pedal. It's missing all the important internal mechanisms. It doesn't explain why this blueberry is blue, or why the ocean is blue, or a flame, or this fluorescent rock. But we're gonna do that in this video, because we're better than all those other videos. Color, for the most part, is the interaction of energy with electrons. That's pretty much it. So we're gonna explain that, mostly because in researching this video, it made me appreciate the beauty of atoms more than at any other point in my life. It also made me appreciate that much of the way that chemists understand the world is by looking at how light and energy interact with things. Chemistry is color, and now you get to experience that too. I drew them upside down. This is indigo, and this is the molecular structure of indigo. It's got lots of carbons, which makes sense because it's an organic compound found in some plants, like Indigofera tinctoria and Indigofera suffructuosa. For this jar of blue pigment to actually look blue to our eyes, light waves from the sun and the lamps in this room are hitting this molecule and interacting with its electrons. So it would make sense that if I change the number of electrons in this molecule, or how they're arranged, I can change its color. Now, indigo is used as a dye and it gives jeans that traditional blue coloring. And part of the indigo dyeing process is reducing it with a strong base, like this. Oh, it's so dark you probably can't see that, but it is getting green. Electrons aren't static singular particles like we think of in a drawing. They move around because they reside in atomic orbitals, these balloon-like diagrams you might remember from high school chemistry. The short version is that orbitals are really just places where the charge of the electrons can be in a molecule, and typically electrons fill up low energy orbitals before they fill up higher energy orbitals. But that's just one atom. When you have multiple atoms connected together, like in an indigo molecule, they share their electrons, and therefore the shape of those orbitals and the places where those electrons can be found changes. We go from atomic orbitals to molecular orbitals, which for the purposes of this story is cool because you can think about the atoms now sharing electrons and passing them back and forth like people passing food around a dinner table. So when light or energy hits an electron, it moves from a lower energy orbital to a higher energy orbital. So now the electron distributes itself differently around the molecule, and you can think about it as if that orbital is changing shape. Now we need to do a tiny little bit of math here to show how this translates to color. And I'm so sorry. I'm also not happy about the math. So this is the energy difference between the low energy state and the high energy state. And it's defined by this. This is Planck's relationship. So delta E is the change in energy between the low energy state and the high energy state. This is Planck's constant, which is basically a relationship between a photon's energy and its wavelength. C is just the speed of light, and lambda here is the wavelength of light being absorbed. And so really the most important point here is that there's an inverse relationship between the wavelength of light being absorbed and the change in energy. That's the main thing here. Big change in energy, small wavelength absorbed. Big wavelength absorbed, small change in energy. So much math for just that. What this means is that the farther you go along the electromagnetic spectrum, the higher the energy and the shorter the wavelength. About this range here is what we can see with our eyes, the visible light spectrum. Longer visible wavelengths that we call red start about 740 nanometers, and shorter visible wavelengths on the violet side end around 380 nanometers. And remember that these are actual measurements of the wavelength of these light waves. The light waves don't have color themselves, but different wavelengths trigger our eyes and visual systems in our brains to perceive different wavelengths. But that's a biology video, and this is a chemistry one. Now, indigo has a pretty small energy difference between its low and high energy states, so it absorbs longer wavelengths around 600 nanometers, which is orange. It's not only absorbing that single slice of the spectrum, but rather a distribution that looks like this, where lots of that 600 nanometer light is absorbed, but also diminishing amounts of the wavelengths around it too. But then basically all of the blues and purples and a little bit of green get bounced back out and your eyeballs perceive the distribution of light as blue. But what it actually means is that electrons are moving through this molecule, changing where charge is centered in the atoms and changing how they're distributed in the orbitals, like inflating the balloon from before. For indigo, scientists think it looks a little something like this, where the lower energy state of indigo looks like this, and the higher energy state looks like this. When 600 nanometer light hits that molecule, it causes the electrons and charge on the molecule to move through those orbitals like this. And unless everyone in the comments has tried to draw an electromagnetic spectrum by hand, I don't want to hear it. That's what's happening when the dye absorbs light. That energy is doing work moving electrons between different molecular orbitals. You are looking at the result of that work. But remember that in the indigo pigment, we could change those interactions by adding a base. Indigo is relatively insoluble in water, so it's often reduced to leuco-indigo during the dyeing process to allow it to dissolve in water and bind to clothing. In this case, reduced means that these oxygens are replaced with hydroxyl groups, which are then deprotonated in the basic conditions. This changes the energy levels of the molecular orbitals and requires more energy to excite the electrons. Going back to Planck's relationship, that means it absorbs light with shorter wavelengths, around 410 nanometers, giving it a yellowish green color. And this is color at its simplest definition. Color is the result of the interaction of light with electrons. Now, if we take that fabric out of the basic solution, it oxidizes in the air and electrons are put back into their original configurations, so we will start to get a beautiful blue color back. And for a long time, that's where my understanding stopped. But then when I was writing the video on counterfeiting bills and started to look into the science of iodine and how it reacts with starch and why the two of them together make this deep color, I realized there was a lot more to color than just that. And I started to do a deep dive on color and electrons and what happens when energy moves electrons around, because that motion of atoms and molecules can result in color as well. That is what is happening in water. Water isn't blue because it's reflecting the blue sky back at you. Sure, on a clear day, there might be a little bit of that, but mostly water is blue because of the way that its molecules vibrate. Take this water molecule with two hydrogens connected to an oxygen. These bonds can vibrate in 3 different ways. These hydrogens can move out and in. These bonds can bend up and down. And there's also an asymmetrical bend where like one goes out and one comes in. So we kind of get something like that. As an individual molecule, these bonds can absorb light in the infrared range, which we can't see. But if you have lots of water molecules together, you change the energy of those vibrations. You multiply vibrations on vibrations on vibrations, and you start to be able to absorb shorter wavelengths of light around 698 nanometers in the red range of the visible spectrum. What this means is that you're taking out a little bit of that red, and so what's reflected back is just a little bit more blue. It's not a lot. That's why the sun reflects really strongly off the top of a lake, but it is enough that you can see just a little bit of blue. And this blows my mind that water is blue because it is actually vibrating. That is where the color comes from. Why did nobody ever tell me this before? This is so cool to me. And this is really hard to see in something like an ocean or a pool because yeah, you can have the blue sky or like blue pool tiles adding some amount of effect. But you can see it in places like glaciers and ice caves where you have really big chunks of ice. You can also see it in a fascinating demonstration from 1993. The scientists took 2 3-meter-long pipes and filled one with water and one with heavy water or deuterium oxide. When they looked through the tubes, the one that was full of water looked blue, but the one that was full of heavy water and had a higher mass and thereby lower vibrational transitions was not. It was more of like this yellowy color. You could actually see the color difference based on how the energy was interacting with those vibrations in the molecules. So cool. Neon signs contain tubes that are filled with different gases that smash into each other. These include, of course, neon, but also things like argon, mercury, and xenon. When you apply electricity to the 2 ends of the tube, those gases inside ionize. They come apart into positively charged ions and negatively charged electrons. You are adding so much energy to those atoms that you're not just moving an electron up to a new orbit, you are actually ripping it off that atom. Those positively charged ions, negatively charged electrons, and additional electrons generated by the cathode fly back and forth across the tube, smashing into even more molecules, creating even more ions. And when those ions and electrons recombine, they have to give off some of that energy that they've absorbed somehow. And they do that by emitting photons of light. This is what gives neon signs their glow. They're actually emitting that energy back out as light. But that is only part of the story. Neon artists quickly learned that they could also coat the insides of the tubes with compounds called phosphors to expand their color palette. Phosphors are a kind of luminescent molecule that absorbs some of the UV energy from those ionized gases and give it back out in the visible spectra. So here, again, you're exciting an electron up to a higher orbit, and then it falls back down and it gives out that light. So in a way, these phosphors are multiplying the amount of light that your eyes see coming from these signs because they're turning invisible UV light into visible light. And we'll talk more about luminescence and fluorescence in a second, because first, we need to talk about fire. In terms of chemistry, fire is the rapid oxidation of a material. When we think of something like a Bunsen burner flame, it's typically the oxidation of something like propane or methane by, well, the oxygen in the air. When that oxidation reaction happens, you get CO2, H2O, and energy. That energy causes the molecules in the flame to vibrate rapidly. Some of that energy is given off as heat, and some of it is given off as light. When you're burning methane or wood or beeswax or anything containing carbon, there's often incomplete combustion products, little bits of carbon that float up in the flame as soot. As those carbon molecules are excited, electrons move up in an energy level and then fall back down. During that fall, they give off light in the yellow range, that characteristic campfire glow, because they are releasing packets of energy as radiation. Those packets of energy are photons, which are massless particles that carry the energy of the electromagnetic spectrum. A photon's frequency on that spectrum is related to how much energy is released during the fall. Basically, the atoms are so hot that they are vibrating so fast that they give off energy in the visible spectrum. And I feel like every good campfire s'more teaches you that that top yellow flickery part of the flame is not necessarily the hottest part of the flame. Lower down in the flame, if the air and the fuel are well mixed, the flame actually gets even hotter, and there are fewer incomplete combustion particles. This means there are no leftover carbon molecules to glow yellow, which is why a good, clean gas flame can actually be really hard to see, like when you flambe something. It doesn't give off much light because it is outputting that energy cleanly into heat rather than vibrating carbon molecules. Instead, the hottest part of the flame looks blue. There, any remaining particles are so hot that they're vibrating so fast that they're giving off a shorter wavelength, higher energy light in the blue and even UV range. But that is different from how an LED works. Okay, so I know that we're not the first video on the internet to talk about LEDs, and this is in fact the best explanation of a band gap that I have seen. Remember those molecular orbitals we talked about before? Let's take the simplest example, 2 hydrogen atoms. Each one has 1 electron. Now, if you combine these 2 hydrogen atoms together, you go from having 2 atomic orbitals to 2 molecular orbitals. 1 bonding orbital and 1 antibonding orbital. Now, each of these could fit 2 electrons, but the bonding orbital has a lower energy than the antibonding orbital, and nature is lazy, so it puts both electrons into the lower energy orbital. But there's always this higher energy one that's empty. If instead you combine 2 atoms with more electrons, things get more complicated. Now, if you think of 4 atoms instead of 2, and then 8, and then exponentially more atoms, you're going to get 4, and then 8, and then exponentially more molecular orbitals. So many that practically they blend together, and you could think of it as an energy band. The highest energy band that contains electrons is the valence band, and the next highest band is the conduction band. The difference between the two is called the band gap. Good conductors like metals have basically no band gap, which means it takes almost no energy to get electrons from the valence band up to the conduction band. The conduction band is like a big, empty, infinitely large molecular orbital. So once they're in that state, electrons can move freely through the material, conducting electricity. They just go from here to boop, and then they can go wherever. Now, semiconductors have a small band gap, so there's a little bit of a hurdle to jump. But if you apply energy in the form of an electric field, their electrons can travel up into the conduction band and through the material easily. By placing 2 differing types of semiconductors next to each other and running a current through them, you can get electrons in the conduction band of one semiconductor to fall down to the valence band of the next semiconductor. And when they do that, they give off photons of light. This is called a light-emitting diode, which is used everywhere. Different sizes of band gaps give off different wavelengths and colors of light. Energy plus electrons equals color. Again, this is color. So neighboring atoms can affect the way that their electrons act together and in response to energy. And that's kind of similar, but also pretty different to the way that all of that works in crystals. We are surrounded by crystals and by electron vibrations. But I swear this is science. A ligand is an ion or molecule that complexes with a metal ion. And look, I can already hear you typing. Biologists pronounce it ligand and chemists pronounce it ligand, and I am a geneticist and that stuff runs deep, so tomato, tomato, ligand, ligand. Just tell me what you say and what your scientific inclination is down below. Anyways, the ligand and the metal ion in these complexes share electrons, so we are primed and ready for some energy to interact with and move those electrons. A nice example is aluminum oxide, which forms a mineral called corundum. When it is gem quality, it is clear. The aluminum ions are surrounded by oxygen atoms sharing electrons, as here. The smallest energy gaps between occupied and unoccupied molecular orbitals require more energy than a visible light photon has, which is why we see this crystal as colorless. But aluminum oxide is the base crystal structure in both ruby and sapphire as well, which famously have colors. You get those colors via impurities. In ruby, about 1% of the aluminum ions are replaced by chromium, which has something that aluminum doesn't: d-valence electrons. Do you remember S, P, D, and F? No? Don't worry about it. They're just different types of atomic orbitals. But d orbitals experience something called the ligand field effect, and they're the reason that some metal complexes are brightly colored and others are not. The oxygen atoms around the metal give off small electric fields. This causes some of the d orbitals to be slightly higher in energy than others. This splitting in energies creates a much smaller gap between orbitals that might just be the right size to absorb visible photons. Rubies absorb short and medium wavelength colors, leaving pure red long wavelength light to be reflected back at around 690 nanometers. This to me is really cool. We are relating this to this. The electronic structure of atoms and molecules creates color. Now, in sapphire, the impurity is copper or magnesium instead, absorbing more of the red colors and leaving behind blue wavelengths. This shows that swapping out the metal ion will affect the size of the energy gap. But there's one other neat thing I haven't told you about rubies yet. They can also fluoresce under UV light. This glass is glowing because of quinine. It's the reason why tonic water will glow under UV light. The structure of quinine looks kind of like indigo, with lots of carbon atoms and rings. But visible light doesn't interact with quinine's electrons in quite the same way. Instead, you need higher energy UV light to excite those electrons. And then they emit some of that energy back out at around 461 nanometers, giving you this really pretty light blue. Now, when you shine high energy short wavelength UV light on molecules like quinine, the molecular structure absorbs that energy. We have seen this before. But in molecules like this that fluoresce, an excited electron loses little bits of energy in non-radiative transitions, basically things like bumping into other things and giving away kinetic energy, before it gives off the rest of its energy as a photon of light. Because it's giving off a little less energy than it took to move it up to an excited state, it emits a photon with a longer wavelength than the one it absorbed. This is known as the Stokes shift. And like with indigo, by changing the arrangement of electrons on these molecules, we can change how they respond to light. So this fluorescent beaker contains another wood extract, narrow wood extract, which contains the fluorescent molecule matlaline. You can see it really strongly absorbs light. That light is stopping like a few millimeters down in that extract. Now, if I take some of this and I add a few drops to another tube, you can see that that matlaline fluoresces really nicely under that UV light. But if I add a little bit of an acid, like vinegar, the matlaline gets protonated, its electron configuration changes, and as those mix, it will lose the ability to fluoresce. I like when chemistry works. Now, this fluorescence looks similar to the bioluminescence found in things like fireflies, but that works in an even different way. In bioluminescence, an enzyme called luciferase oxidizes another molecule, and then that energy is given off as a photon, efficiently converting that energy into light rather than heat. Biology is cool. But that's not even the weirdest way that biology can make color. Take, for example, the blueberry. It is not explained by a single thing we've talked about so far. Sure, blueberries look blue, but if you blend them up, you can see that the pigment molecules inside are actually purple, not blue. The blue doesn't come from a pigment molecule. It comes from a waxy coating on the outside of its skin. Man, and as this dries down on the paper, you can see it turning from a purple to a blue. I think this is that wax, like drying out on the paper. That's kind of crazy. This is structural color. It is the same mechanism that gives some butterfly and bird wings their color. Tiny nanostructures created by the waxy coating of the blueberry or the keratin of a bird feather or the microstructures of an opal bounce light off of the surface. The cool thing is that when the researchers studying these blueberries dissolved the waxy coating off of a fruit with a similar property, an Oregon grape, they created a colorless liquid solution that, when dried back down on a glass slide, was blue again. And to explain why that's possible, we have to back up to what light actually is. Waves of electromagnetic radiation. When light reflects off of a smooth surface, it bounces in a predictable direction. When light reflects off of a disordered surface, it scatters. But if that disordered surface has gaps that are just the right size, certain wavelengths will match up perfectly so that those waves add together, otherwise known as constructive interference. The ones that don't match up will cancel themselves out, which is called destructive interference. And because these structures are nano-sized and wavelengths of light are measured in nanometers, the interference lines up just right to be interpreted as color by our eyes. What's even cooler to me is that disordered coatings, like the blueberry wax, give us angle-independent color, which means it looks the same from any angle. But a more ordered structure, something like the butterfly wing, can give us angle-dependent color, since the wavelengths that constructively interfere depend on the angle the light is reflected at. This is what makes some bird feathers, beetle wings, and stones iridescent. And constructive interference is what makes soap bubbles iridescent too, except in their case, it is the constructive interference of light bouncing off the top and bottom edges of the soap film that we see with our eyes. So cool. And it's all beautiful, really. And I don't want to get too philosophical here, but energy from the electromagnetic spectrum is bouncing all around us all the time. There are X-rays and gamma waves and microwaves and light waves just bouncing all around us everywhere. But we have evolved an organ that allows us to see just a fraction of that energy. And what we're seeing is typically the interaction of that energy with electrons. Electrons are moving and changing and doing work because color is chemistry, and chemistry is color.